Okay, I'm sorry, a little bit 1 minute late, I guess. So you guys can hear me? Like,
yes, we can.
Yes. So so what I'm going to do, like today, I guess I will start with like talking about homework, and so I guess probably you guys will be interested. And yeah, we can start from there basically. So I may not go for each of the questions, but I will go for questions that I think like most of you guys will find interested, by interested, and maybe I adjust my mic. I don't know, not sure if you guys can hear me clearly. And let's see. And maybe I will talk a little bit more about, excuse me, about like Markov model. Because reading your solution, I realized that like maybe many of you are actually not familiar with that, and it's fair like we never talk about that. But at the same time, I've realized that like I haven't taken any engineering course, like courses like electrical engineer. People like my professor will like talk about that in detail. I'm also like when I taken, actually I've taken like 2 information theory courses. I actually just one, but I sit in another one. But the professor also like never talk about that in detail. But but I guess maybe I will try to do that, like just do something pedagogic. I'm not sure like how good I'm doing that, but and I will use the language may not be canonical to statistician and also like computer scientist. I'm more like from the background of an electrical engineer. So so let's see. Let me. Yeah, let me share. Share whiteboard first. So so let's let's start with the problem itself. Like so, we have the problem like oops. So with that tropical island problem, I guess it's good to use that to motivate the Markov model. So I'm not sure how many of you guys like remember and know finite state machine. I think this is something I learned at like in undergrad. Like I don't even remember what course I talk about that, but it's just that you have kind of like a kind of model that like or a system with like a number of states, then you can hop from one state to another state and so on and so forth. And when you hop from one state and another state, probably like, yes. Any questions? So whether you will hop to this state or like hop to this state, let's say, it depends on like the input, let's say, right? So there may be some input. Given the input, will determine like whether you go to this state or the other state. So wait a sec. I want to make sure I'm recording. You said. Yeah, that's good. And what we're interested in is a probabilistic finite state machine. So in the sense like you may have input or maybe may have no input, but in either case, like even when you have an input, like maybe for both from this state, like maybe S0, I go to this S1 and S2, and even I have the same input, like let's say 1, I don't know for what, but this would be a probability that like even with the same input, I can jump to this state, maybe with some probability P, and jump to this state with some probability 1 Q, let's say, and maybe it will stay to itself like with probability 1 minus P minus Q, let's say. Now, go back to our homework problem there. Like we also have this kind of finite state machine, right? And probabilistic finite state machine. So we basically only have 2 states there, right? We have like the state is like basically is sunny or rainy for a given day. And then like there's a transition that's no input there, but that will be we'll have a probabilistic transition that from a sunny day to a rainy day, and then sunny day stay in sunny. I think it's like this is like 95% stay in sunny, and maybe 0.05. I remember the numbers like that. And then rainy, like that will be like 20% of the chance will be like stay rainy, and then like 80% of the chance will stay sunny, right? Something like this. and of course, this model actually by itself, like this is like every time like you see a state model, like this probabilistic state model, you know there's some Markov thing going on basically. The Markov in the sense like if you think of like you for example, like you start with like the weather at here, like first day, like 0 day is like sunny here. And then like next day maybe it's still sunny, and then maybe like the next day is still sunny, and then like the next day I'm rainy like here, and then next day I go back to sunny like here. Now when I think of like what's the chance that I'm staying, I have this W3 at day 3 to be sunny, that only depends on my previous day, right? Or I should say like knowing that like my previous day is rainy, like W2 is rainy, I don't actually care like what's the weather before like my previous day, right? And this is exactly this kind of Markov property, and this is like actually sometimes you also see like this kind of Markov model essentially say this the same thing, and sometimes people refer to this Markov model. Oftentimes, like when you're at different states, you also have some kind of oscillation you can make. For example, like in this case, exactly, we have this kind of also it's precisely like in our homework problem there. We can observe not just the weather, but also we can observe the actually, of course, we have this so-called hidden Markov model. I guess you guys heard of that. So when we have hidden Markov model, maybe let me start with this Markov model first. Like in this case, of course, this itself is already Markov model, but oftentimes I want to say Markov model, you can also have some kind of oscillation. Like in this case, for example, I am in state S here, like when the weather is like, why it's become, yeah. When the first day is sunny, maybe I have I can kind of observe the current temperature, like for that day, right? Maybe the temperature is 27 degrees, and then like the second day is 28, and then like the next day become rainy, it's only 24, like maybe then like it's sunny again, like it's like 26, let's say. Now, the difference of like hidden Markov model is like this is itself is a Markov. Maybe like before talking about hidden Markov model, let me kind of like and disentangle like this stays here into like a timeline. Let's say I have like W0, there's like weather first 0 day, and then W1, W2, and W3, right? And then like this first day here, I observe like this is sunny, and this one is sunny also. This is rainy, it's sunny. And also I observe like temperature, like T0 here is like 27, like T1 is like 28, T2 here is like 24, and T3 here is like 26, let's say. So I can disentangle this into this timeline here. It's more easy to analyze, I guess. And you can, when people say like hidden Markov model, like a very much like a typically what people are referring to will be like something very similar to this but you have like this states here, like some of these states are hidden states. So this will be like hidden states. For our problem here is like it's not exactly a hidden Markov model because we can observe the weather as well. But for hidden Markov model, like you won't be able to observe this thing here, but you are able to observe like this temperature here. So is that all clear up to now?
So just the temperature portion is the hidden state?
No, this part is observation. So maybe I give an example, like you will be more familiar with communication engineer. So let's say if I send through something through a channel, let's say, and I have something X, let's say this is a going through a channel, I have Y here, and this is X1, Y1. So you have like basically like you have like let's say like you are passing through this sequence into a channel like X1, X2, and so on, X3, X4, like, and then you want to recover this the Y1, Y2, Y3, Y4. I'm sorry, like it's not recover, but you observe this at the end of the other end of the channel here. So you have like let's say X1, X2, X3, X4, right? That's like what you send through the channel. And at the decoder side, you don't know that, right? You cannot see that, right? But what you see is this Y1, Y2, Y3, Y4, right? So then this would be the hidden state. You can consider these are the hidden state. And these are the observation here. This is the hidden state. So again, this will be a hidden Markov model. Like, again, I want to emphasize this. If you don't know the weather, if like in the homework problem, we can observe the weather. If we cannot observe the weather, then it's not a hidden Markov model. Sorry, if you cannot observe the weather, then it will be a hidden Markov model. But now I can observe that, like strictly speaking, like basically it's not a hidden Markov model because you don't have hidden states here. But this hidden Markov model, you can see it everywhere. Actually, it's very common. Basically, if you have like a time sequence, something like some time sequence signals, but what you observe is only a noisy version of that time sequence signal, then more or less you can represent it in this hidden Markov model. So is that clear? Kind of.
Yes.
Yeah. So then back to here, one thing I want to emphasize is that given this hidden Markov model, there's always some Markov chain is going on. That's so have some Markov property with respect to these variables here. For example, like I can claim that like I have some Markov property of this like W0, W1, and W2 here. And maybe I change the color. So these guys here will form a Markov chain, basically. So forming a Markov chain is basically the same as saying that actually I can write a longer chain like W3, W4, all these I form a Markov chain. But when I say form a Markov chain, basically meaning that like given that everything like in the middle, the variables on the two sides are conditionally independent. So or like maybe I look at this one here, maybe this one, given W2 here. If I try to, let's say, this is something I'm interested in the future, like W3 here, given W2 here, as I just mentioned earlier, everything before that will not be important anymore. And this is basically, oops, capturing the model here. It's need to be careful that like we are not saying that this model is correct. It's just like we model it this way. It's basically like, for example, you think of like in reality, like maybe we can argue like many times that Markov model does not make sense because most likely today's weather will not just depend on the previous day, but maybe only depend of the day before. For example, like if I have a hurricane going on, then probably that for the last 2 days, I will both were rainy. If like both last previous 2 days are rainy, then it's likely like because there's a hurricane, right? Then there's a good higher chance that today will also be rainy as well. So, but in the sense that okay, you can build like more complex Markov model. For example, like I can have my variable not only depends on the previous state, but also like depends on like previous 2 states. Then like this will be a second order like model, second order Markov, and of course in the same manner, like I can have like depends on 3 more previous states, then will be like third order Markov and so on. So and let's see what else I want to say. Okay, yeah, maybe like I saying that like I just want to make sure that like it's capturing the model. Like so what I'm saying, like given this one, these two will be conditionally independent, right? So let's see, I have how do I model like PW1, W2, W3 here? You remember that like from our model, like we are modeling that as a P W1, or let me write it like this way, like just more direct. How do I model like W2, W3 given W1? So in our model, we actually basically model that as a W2 multiplied by the given W1 multiplied by the probability of W3 given W2, right? So, but at the same time, so you all agree with that? Like this is like how we define the model basically. And by base rule, like this also is always true to be like this is equal to PW2 given W1 times PW3 given W2 W1. So meaning that like this guy will be equal to this guy, right? Yes. So yeah. Yeah, you can ask question, yeah.
Just one question. I'm not really sure how relevant that question would be with regards to the Markov model, but what would that particular model be called if the probabilities given for the state are also varying with regards to time?
Oh, say that again. Like
so yes, we have suppose with regard to our homework assignment, we had sunny or rainy states, but they had their fixed probabilities of 0.95, 0.05, 0.2, and 0.8 respectively. But if these probabilities are also varying with time, so is there any particular type of Markov model?
okay. That would be
That's the question. I'm not sure how relevant is it.
yeah, that won't be a stationary model. So if you remember like maybe taking some class in like stochastic processing, they definitely will talk about something is like whether something model is like stationary or like Y sensationary, so on, something like that. So if your probability is changing over time, then it won't be stationary basically. So this is Y stationary. So if your probability can be changing, but the mean and the variances I keep the same like over time, like kind of like in a higher level, like we'll be calling that like Y stationary, or more precise, it should be like I will consider like the yeah, I guess it's good to just like call it like that. But yeah, in a short answer for your question is like it basically you will consider it some non-stationary model.
Okay, sure. Thanks.
Yeah. So, but of course, I love things like stationary, but I guess it's fair like to assume in a short time frame, just assume it's like kind of stationary. That will just make your life like easy. So, but like in a longer time frame, you can just like keep something adaptive. Like every once in a while, they try to estimate the statistics again. But over that short period of time, you just assume things to be stationary. Yeah. So that's I guess like company people what they will do. So I guess like Mookie also like raise your hand. You have another question?
Yeah, I initially got confused with the derivation that P of W2 comma W3 given W1. You wrote it as P of W2 given W1 multiplied by PW3 by given W2. I didn't understand why you wrote that, the second line.
Oh yeah, this is like precisely how we model that, like because like we only we say in the problem, we say, okay, for today, let's weather, like we only depends on the last day weather. Basically, that's how we model that problem at that time. So, but if we give this assumption, then we immediately have this Markov property. You can see it's basically, if we look at any variables here, like W3, and when I given a previous day like variable, then like any variable like before that will not be important. Actually, I can, of course, like this will be saying like this will be equal to that, but you can pad like all these previous variable. Maybe I can W4 given W3 here will be just equal to W4 given W3, W2, W1, and so on and so forth. And also know that like I can use the same kind of yeah, you can show it in the similar manner that like I can have W4 given W2. This will be like the same as W4 given W2, W1.
Would P of W4 given W2 would be equal to just PW4? I mean, if it does not give any, sorry, it does give us a little bit of information, right? Given W2.
Oh, this yeah, this will give you information like given W2. I'm saying that like given W2, W1 is not important anymore. So if you don't know what's going on like yesterday, but you know like what's going on the day before yesterday, then the day before yesterday won't be important anymore. It's that the day before yesterday, yeah, it won't be important anymore.
Got it. Thank you.
Yeah. And can you show that like maybe I won't ask you to show that. It's very simple. If you don't feel comfortable with that, you just can like, for example, like write out this like W4 W2 as like W4 W3 W2 and some of the W3 and something like that, and then like and then of course like this model will be W4 W3 P W3 W2 and so on. Then you use the same argument like this one here. It will be the same as PW3 W2 W1, and then you get back the term together, we'll get back this one, something like that. So, but again, what I mean is maybe I just do a quick summary here. So if I have a Markov chain, long Markov chain here, so given this guy here, or like I should say given this guy here, so given everything in the anything in the middle here, like anything on the two sides there will be independent, will be conditionally independent. Okay, by the way, like I just want to make sure like I guess I talked about that before, but when you have when you have this condition, you can immediately show that like this is also imply like PW3 W1 given W2 is equal to PW3 given W2 times PW3 given W1. So it's like conditionally independent. W2. So, but you have to be very careful though. For example, like okay, maybe I have a question 1a/b part here. So, for example, I have a Markov model here. Like let's just take this one here. So maybe yes. Okay, I have another question. Yeah.
Yes, sorry, I had another question. In the equation you wrote P of W3, W1 given W2 is equals to W3 given W1 multiplied by W3 given W1, or is it? But it should be W2. The last term.
You mean here, like where? Like,
yes, yes, the last term. P of W3 given W1, or it should be W2.
Yeah, probably it's typo. Like, yeah, it's just wait a sec. W3 given W2 and W1 W1 W2. Yeah. Yeah. Thank you. Yeah.
Okay. Okay. Now got it. Okay. Thank you.
So let's see. So W1 W2 T2. So is this a valid Markov chain? Do I have this Markov chain? And also, let's say W1 T1 W2, do I have this Markov chain? So this is a true or false, a true or false question. Okay, you guys are here, like so the question is like we're just talking like this Markov chain. So when we say this Markov chain here, this is like the same as, always remember when we have Markov chain is exactly the same as conditional independence. When I say something like W1, W2, and T2 form a Markov chain, it's also the same as like I'm saying like W1 and T2 are conditionally independent given W2. And now this is also the same as this. Basically, you can verify with this condition, something like that. That will be equivalent to saying condition like P W1 T2 given W2 is equal to P W1 given W2 times P T2 given W2. Yeah. And also like this condition is also the same as a P W1 given W2 T2 is equal to P W1 given W2. We have showed that before, like in one of the earlier class. I guess I won't show it again. So you can easily show it like with a couple of steps there. Yeah. So I guess I guess I made a point, and most of you, I see like probably all of you guys are correct. So I just a quick look there. Yeah. Yes. So then immediately, I guess a consequence of like Markov chain and conditional independence is that like when we have something like this, let's say if I have this Markov chain property here, like this one. So the conditional entropy, like let's say HW1 given W2 and T2 is just equal to oh, okay. Let me try to explain this. This is actually from the model itself. So this is also like how we describe the problem, like the model. So we can verify this way. So we can verify, let's say, how do I write, let's say, T2 W2 given W1. How do I write this? How do I build this model? In our model, like we say that like the temperature only depends on the current weather, right? Or the weather of the current date, right? And also like the weather of like today only depends on the weather of previous day, right? So therefore, like this one is actually like will be, I can give something like, let's say W2 is like sunny, this is sunny, this is like 27 degree, whatever. This is actually just equal to P, W2 is sunny, right? Given W1 is sunny, time P, T2 is 27 degree, given W2 is sunny, right? So whenever I write that, this already, by the same argument I have earlier, maybe I shouldn't even write that. This looks a little bit hard to read. Let me take it back, like not to write this because it's easier to read this, like W2, W1, right? T2 given W2 here. But by base rule, like this guy here, right? Base rule is actually equal to W2 given. So you mean that why I have this guy here? This is actually from how we describe the problem, basically. Yeah. Yeah. Okay. That's good. So, but okay. Let me compute it like for the sake of like okay, completeness. Okay. So again, like by base rule, this guy is equal to this one, right? So therefore, I will have like I just cancel this term, two terms here. I'll have this guy happening, right? So I will have this one happening. So that's basically, yeah. Okay. Let me. Yeah. Of course, I have this another equation is here, but Markov chain is symmetric, right? So I have a Markov chain like W1, W2, T2 here that can either give me this equation here and also give me this equation here, W1 given W2, T2 is equal to W1, W2. So, but let me look at this equation. Okay, let me look at this equation here. So go back, I just focus on one equation here. Now, if I look at this equation here, I'm thinking maybe the other equation is better because that's is that what we asked in our homework problem? Let's say I forgot. Like we asked about. So actually, it doesn't matter. Let me just go for this one first. So then this one here, like what's the expectation of? Sorry, what's the conditional entropy of W1 given W2 T1 will be expectation log W1 given W2 T1, right? T2, right? Now, but we are saying that like this is equal to this guy, right? So therefore it's equal to expectation minus log W1 given W2 here, right? And this is just equal to HW1 given W2. So this is again, like very intuitive. So if we are talking about like what's the remaining information of W1, knowing W2 and T2, if I have a Markov chain, then it will be the same as like the remaining information of W1, knowing just W2. It doesn't matter. Like once I know W2, I don't care about W2, T2. And also remember, like this is actually the difference of these two guys are the conditional mutual information, right? So I actually have like I, W1, and let's see, T2 given W2 is equal to HW1 given W2 minus HW1 given T2 W2, right? So now I'm saying these two terms are the same. That means that the conditional mutual information is equal to 0. And it's again, like, this is like we elaborated last time also. Like when we have like W1 and T2 are conditionally independent. I don't quite. So how long had that comment? But I'm not sure like what you're referring to, honestly. So we have like this. You're referring to earlier question? No. It cannot be, right? So okay, this won't be equal to 0. If it's equal to 0, it means that like you knowing tomorrow's weather and also the temperature, then you know precisely the weather today. This is not how we model it now. And probably like you will never model something like that. No. You know W2, okay. That you need to be very careful. Like you have the probabilistic model. It does not have causation there. Like you never model causation in the probabilistic model. And that's I studied, like trying to do that. Like a very famous UCLA professor, like spent his whole life doing causation, like in probabilistic model. But in general, like when you do a probabilistic model, that's only correlation. There's no causation. You cannot the canonical model that everyone use does not put causation there. When you say like what's HW2 given W1, that's no. You're assuming that like you are blind yesterday. You are not given that information yesterday. Now you know what's going on today. Now you just want to like figure out what's yesterday. So it's fair. It's sometimes a history like just happen. Like if you miss that information, you miss that. Like you cannot always know the past. So did I answer your question? So in general, like you cannot say like because it's the past, I will just know that. So I won't have like HW1 given W2 is equal to 0. No, you don't have that. Like the notation here is just assuming that, okay, I know what's going on like tomorrow, or like if assuming today is day 1, then but I'm kind of like, or maybe you can think of like today is like day 2. I know what's the weather today, but I'm not here. Like I was not here yesterday, and I don't know what's the weather yesterday. And I want to, based on like the probabilistic model, I want to figure out what's the weather in yesterday. And the amount of information needed for me to represent that information will be like HW1 given W2 bits. So is that clear? Where am I? I'm thinking. So we say, we say, okay, then this is like, okay, we talk about this conditional mutual information. So when the conditional mutual information is equal to 0, also like another way to verify that the the variable are conditionally independent given given whatever the variable in in the middle of the Markov chain. So I guess at that time it's probably become pretty clear for one of the question in your homework problem there that I guess you're asked what is like the conditional mutual information between, I guess it's T1, T2 given W2, something like that. We can extend whatever this Markov chain actually. For example, I can have this Markov chain, non-Markov chain here, W0, W1, W2, W3, W4, or yeah, something like W5. Generally, what it means like when I write something like that is that given this variable here, then any variables here, MD here will be conditionally independent. So this, I said, what way oh, wait a sec. Is D part? Yeah, that's a D part homework too. Yes. When I have like, yeah, the W1, it may be W1 or W2. Oh yeah, okay. We are going to discuss. Okay, let me finish. I'm sorry, I answer one question at a time. Let me back to sales question first. He had that question first, but I mean, I have this long Markov chain here. It basically saying that like I will have, for example, like W0, W1, and W2, and the mutual information of all these three variables. So therefore, be careful with the grammar here, the punctuation here. I have to be comma here. It has to be semicolon. And the mutual information, conditional mutual information, W0, W1, W2, and W4 and W5, given W3 will be equal to 0. And I can do whatever I want. And sometimes you can even have train something like that. So maybe I write like this. So, okay, this will be a difference. I try not to confuse you. Let me write another example. Let's say I may have X1, X2, Y1, X3, X4, let's say. Then know that like if I write a chain like that, I will have X2. Okay. I need to put my mic. Okay. Yeah, I guess it's stable now. So I will have like mutual information like X1, X2, give MX4 given like Y1, X3 are equal to 0. But be careful that like when I write a chain like that, I may not have given Y1 equal to 0. This one can be non-zero, something like that. But I will have something like X1 and Y1, X3 given X2 is equal to 0. So, okay, now I guess, Sale, do you still have question with that? Like, I guess it's pretty clear. You can write this chain as long as you want. So, but it's just a representation. You write the chain there. It just represents like conditional independence among the variables, basically. So I'm now back to that homework problem here. I forgot whether it's this one or like ITCOT1 given W0 or like it doesn't matter too much. I think like I can change it to W2 here also. But the point is like you can see that like I have a Markov chain here, right? I have a Markov chain T1, W1, W2, T2 there. And given that, like, so since I have Markov chain like that, if I given W2 here, this and this will be conditionally independent. So therefore, actually, I can quite right away know that this is equal to 0. Just knowing the structure of these variables here, there. And of course, I can verify that also, like look at like this this way as like HT2 given W2 minus HT2 given W2 T1 there. But I can pretty quickly also say that this is actually equal to this guy here. So because like, first of all, let's see how I'm going to do that. Let's see, let me try to see, like I basically need to show this PT2 W2 T1 is yeah, it's a bit elaborate to show that, but it's not hard to show. What I need to do is I will pad like a bunch of variables here. Probably I want to also put in W1 there. Wait a sec. Why? Wait a sec. Yes. So of course I can just do from first principle. That is like PT2 W2 T1 over P W2 T1 here. Oops, let me get better handwriting here. So let me. So PT2 given W2 T1. So this I need to consider PT2 W2 T1 PW2 T1 here. And let's see. And I will have let me also introduce like okay, I want to give up, honestly. Like this is a bit it's a bit painful. Like T2 W2 W1 T1. I know I can do that, but it's probably like I'm not sure it will be worth going through that. But yeah, hopefully you see my point. Like I can do like that. Then when I split all these variables here, then you will have something got cancelled eventually. Like you will just get it back, like just PT2 given W2, something like that. But so but you can just go back home to try to verify that. But you can take my word, just say from the model itself, because you can verify that's the Markov chain there, this will be equal to 0 actually. And so let's see. Okay, let me see what's the problem there. Oh, okay. Maybe also one thing like for this model, I guess is at least a couple of you don't know the steady state probability. Maybe like I just mentioned, this is in the homework one there. So when we have a why was QB is false? Wait, what's QB again? Oh, okay. I have something like that. I guess I have something like that when he said like W1, W2, T1, T2. I don't remember the exact question there, but I asked the question, it said something like W1, T1, and W2 there, like whether we have Markov chain there. Actually, you can try to verify that. Like, so if this has to have a Markov chain, so yeah, let's see, I need to pull down to show your message. Yeah, okay, yeah, this is different. This chain does not exist. Of course, you can verify that, but in general, like you think of like the Markov properties coming from a process that that okay, after all, you think of like you can figure out like when you are going to have a Markov property is like if you are considering the last variables here, and you think of like, okay, if I know this variable here, will it help if I also know the variables before that one? If it helps to know like also this guy, then a Markov chain does not exist. If this one, this additional one does not help, then this Markov chain will exist. So in this case here, like if I have W2 here, I'm knowing this temperature in this previous day here, that I'm not 100% sure like what will the weather like the day before. I mean yesterday, right? I know the yesterday weather, like let's say yesterday weather is 26 degrees. I mean, you remember 26 degrees, like I think in the problem, in the question set up there, like it can still either be windy or sunny, like with some probability. So I cannot say for sure whether it's windy or sunny before. I mean, basically yesterday. So of course my model, like today's weather is completely depends, no, I shouldn't say depends, but like conditionally depends on like the weather like the day before, the weather yesterday, right? So therefore, like since like only knowing T1 or like knowing yesterday temperature does not give me a precise does not tell me precisely whether yesterday is sunny or rainy, then if I know also W1, like if I know precisely it's like sunny or rainy, then like it's going to help. So therefore, this Markov chain should not exist. Yeah. So yes. And now let me, okay, I was talking about steady state probability. So the probability to know sunny and rainy in this like probabilistic finite state machine, I call it, or like all this Markov model, like you basically you can assume that each of the state have this some steady state. So I have like this probabilities like PS and PR here is the steady state here. Maybe I cap out here PS and PR. Now there's some transition probability, right? So if let's say like if I have maybe like I have my current so I want to say like this is like conceptual, like it's not really for real. But let's say I think of like last day probability, like PS here, and if this is the steady state, or like I think of like what will be the think of the probability flux, like I have some probability flow here. So if my previous state has some probability PS here, and then in the next day my probability will be equal to PS times 0.95 plus PR times 0.8, right? Something like that. And this will be the same as like today if it's not going to change. So therefore I will have something like that. Then basically if you just rearrange the term, I will have like PS 0.05 is equal to 0.8 times PR. So that's precisely think of like you have the flux, like this is like going out will be like PS times 0.05, going in will be like PR times 0.8. So the flux should be balanced. So if this is balanced, then it will be a steady state probability. And these people, this is a balanced equation. And if you have a lots of states here, like maybe I have like state S1, S2, S3, S4, and people call something like detailed balance equation, just meaning that like if I look at like something going back and forth, like out of the state and in going in of the state here, actually not exactly. Actually, if you go think of like a pair of states, there's some probability flux going in and probability flux going out. If this probability fluxes, I don't know, like balance each other, then basically we will have a detailed balance equations. And in that case, I will just assume every equation got balanced, then we will get some steady state probability. So that's one way to find the steady state probability. So it's just a remark actually. Like if you never saw something like that before, like it's just a remark. Maybe you have already. So okay. Let me repeat it again then. So you think of like conceptually, okay, you think of like this is like water flow here, like you think of some probability. So I would say it's kind of like not real, honestly, but it's good for just as a way to kind of to manipulate this thing like easily. So you think of like, okay, I have this probability steady state, then hopefully this probability is not going to change, right? So in the sense that you think of like maybe today I have like PS0, like maybe now it's today is 0 state. I have like so much probability on here and so much probability here. And then in the next day I have PS1 and PR1 and so on, and PS2 and PR2 and so on, right? Now, how this probability will change will okay, we can just look at this model here. If I have like PS0 in the 0 day and PR0 at the 0 day for rainy, then for the next day PS1 will be equal to like this PS0. I have so many I will going back, like I will have like PS0, like 95% of going back to 0, right? Then I times 95%, right? Or like times 0.95, plus like there should be also probability coming in from like from the windy, from the PR0, right? So I have PR0 multiplied by 0.8, right? So then I just say, okay, this is if this is really steady state, what I want is that these probabilities are not going to change, right? So it means that I want PS1 will be just equal to PS0. So then if I have PS1 equal to PS0, this is equal to PS0. So then I will just have like PS0 0.05 is equal to 0.8 times PR, maybe 0.05 multiplied on this side, 0.05, 0.8 times PR0. So, but what are these things? It's basically, it's like PS0 times PS0.05 is how much probability going out of like stay sunny, right? On day 0, on day 0, yeah, on day 0, right? And PR0 times 0.8 is how much probabilities is coming inside, coming into like state 0, right? So if we balance this, then we will have the steady state probability, right? So we want to have this is equal to that, then, and you can balance each of the pair of the nodes. If you have more nodes there, assume you have a many state model, and of course, like sometimes you cannot balance that. This detailed balance equation will only work with if you don't have like something like this. But many problems like that you can actually work with detail like this one. You can do this detailed balance. But this is actually, I mean, maybe I don't even should mention this detailed balance equation because it's not really important. I mean, this concept that like you're from one the current day, the probability is not going to change in the next day, that is sufficient. Actually, you don't need to care about the rest. Because oftentimes, like another way I see some of you guys do it also, like maybe it's an overkill way to do it. It's like you can just like write down the probability and the transition probability in matrix form, right? So I can have a vector of these probabilities here. So my 0 state probability will be just a vector like PS. I have this P0 will be a vector, right? So as a PS0 and PR0. Now, how I'm going to transit to the next day probability will be just like multiplied by by transition probability, a transition matrix, right? Yes, you can use the. You can also like consider this size. I'm not sure like where do you get this equation, but if you consider this size here, it's supposed to give you the same solution. Yeah, you should get the same solution. So if I consider not the node here, I consider the node here, then the probability going into R is like. Yes, that's why I'm saying this is all conceptual. There's no initial probability, right? Because if you think of that, but it's convenient like to find this steady state probability. In reality, like what's going on is like you just at this state and you move on, right? There's no probability flux there. But it's really convenient to think of it this way than to find the steady state probability. And the steady state probability will basically will be the probability. Think of like you play with this model here, like just we just need 2 successive days here because if you are from here transit to here, you're not going to change. Then from P1 to P2, you're not going to change also, right? Because then your PS1 and PR1 here is just equal to PS0, PR0 here, right? And from here, because this thing here is not going to change, then this is also is just equal to PR2 is just equal to PS1, PR1 is equal to PS0, PR0. I mean, the steady state probability makes sense only when your model is actually not stationary. Then we really should talk about steady state. But here, like if everything is stationary, yeah, actually maybe it makes more sense when we think of like to start from the beginning. If like something is non-stationary, then maybe your model is like can keep changing. Then maybe your probability is kind of catching up. Then because I suddenly you change the transition probability there, then your what I mean is like maybe suddenly you change the weather here, the condition here. No, I shouldn't say it's change the weather, but I changed the transition probability here. That's like as high a chance to get windy now, right? It becomes 0.15, let's say here. This becomes 0.6. Now suddenly the probability will change, right? Now maybe it used to be like I have like 0.96 probability that like it's sunny, then suddenly slowly my probability will shift to maybe like 0.8 or I don't know to be sunny. But if your model is stationary, then like that steady state probability doesn't really, it's not really that relevant. Yeah. Yeah, I hope like I didn't confuse you more, but I'm not sure I should compute this, so maybe I compute this one. So if I have the probabilities here, this is the previous day, I can make it as a vector, and the next day I just also write in a vector. Then I can just write a matrix form, right? So in this case, the next day probability PS1 here would be just equal to 0.0. Let's say I shouldn't change this number now. Let me give this back. It's 0.8. So I have this PS1 is equal to PS0 times 0.95, and PS naught is like 0.8, right? And this is like 0.05 and 0.2, something like that. Right? So then if I want to have like something stationary, I want to have this day, what is that? Like I will have, this is a, I just call this P0 like as a vector, this is a P1 as a vector, right? And maybe I write this as T as the transition probability here. Then I will have like this P1 should be just equal to P0, right? So then I will have, maybe I just write P0 is just equal to P, I don't know. And have like P is equal to TP here. That means that like, that means what? That means that like, do you recognize something? This is actually, P is actually eigenvector of T with eigenvalue 1, lambda is equal to 1. So that means that like, another way I see like some of you guys solve that, I think it's definitely overkill, is you build the T here and then try to do eigenvalue decomposition and find this. But that's definitely is a good way to do that, like especially when your model is really big, like you have lots of states. Then one way you can do it is just build this transition probability matrix, and that's actually how people did it. Like, what's that? Google, there's a, I forgot, like the first search engine, like they introduced is based on that. Like they build the transition probability, like they predict like what's the probability you transit from one page to another page. Then, yeah, actually this is interesting. What's they call it, like what's the creator of Google? Like, can you guys tell me? I forgot the two creators, the graduate students from Stanford. I forgot the name. Do you guys know? I certainly Larry, yeah, I forgot it's a page search, or like I forgot it's whether called page search or like the other creator.
Larry
But
Page and Sergey Bin, I think it is.
It's a page search. Yeah, the idea is super simple. It's exactly the PageRank. Yeah, exactly the same. I mean, it's exactly like that. So you have this model here, right? So wow, that's great. I digress to PageRank. I guess people are interested, right? So but this is exactly the same thing here, right? You're just computing the steady state probability. You basically build a model of transition probability. So you have like many pages here, right, in the internet. So you can one page hop to another page and so on. You just look at each of the link here, and you can estimate what's the chance that like you from one link to another link, right? Then it will be exactly the same finite state probabilistic finite state machine we have here. Then now for each of the page, if you have a good estimate of this T here, then you have a big T matrix here, right? Now then, what you need to do is simply find the steady state probability. So like, if you have a large steady state probability, what does that mean? It's basically meaning that like you have a large chance of staying in that page, right? So that means that page is more popular. So that's how they do that. Like, so then they first predict this T here, then they solve this problem here to get this P, and then they just rank it. So basically, like you have the highest one will be the highest probability. So any question with that? Of course, you can, instead of solving this, of course, okay, you look at this, as I said, like this is just an eigenvalue problem, right? Because this is just you have a matrix multiplied by this vector. If you remember this, like Tx is equal to lambda x, it's just like you have basically saying this is an eigenvector of T with eigenvalue lambda, right? So I have something like this. It's just saying that like P is an eigenvector of T with eigenvalue lambda is equal to 1. So we just solve the eigenvector P, then that's our solution. And in practice, because T is huge, you may not be able to solve that just solving like eigenvalue decomposition, like plugging into MATLAB would be too big, the matrix. But the simplest way you can do it is like you start with some random probability here, and then you keep multiplying that, because you have like, you expect like TP will converge, right? You have TP, I hope that will get to some P here, right? So I just iterate. I have like P1 is equal to TP0, and then I iterate back like P. Basically, what I mean is I have PK plus 1 will be white like this, right? So then you just keep multiplying that, then you'll get like final PK plus 1 there. Super simple. Yeah. So any question with that? So let's see what else I like to talk about. Well, we will talk about that, and maybe I should go to look at. Okay, maybe how about I give you an exercise first, then just because I see that like you guys are, honestly, most of you guys are not, yeah, but to be fair, like this is all new concept, right? When you compute the conditional entropy and so on, like most of you guys are still a little bit stuck. So maybe it's good to do a couple more exercise. So I have like using that same example, like in both homework 1 and homework 2, maybe you guys try to compute like HW2 given W1, W3. This is, let's say, question 2. Oh, I guess this is a good time for break also. I guess maybe it's not fair, but maybe maybe we have like 15 minutes. Like maybe we come back like, yeah, maybe a little bit more than 15 minutes. Like, so you work on this at the same time, like, so maybe we come back like 4:30. So, but I'm around, like you can ask any questions. Let's see, dependent on mutual information, W1, W3. Okay, so let me make sure my handwriting is like, I know my handwriting is bad. So it's like W2 and W1, W3 here. That mutual, I'm not 100% sure, like your question, honestly. Oh, it's not, okay. This is entropy here. So yeah, know that like only for mutual information, we have semicolon in the middle. So for entropy, it's always like just comma. So this is just meaning that like the entropy of like W2, conditional entropy of like W2. You know, again, like you can roughly think of like what's the remaining information of W2, given that you already know like W1 and W3. Actually, how about that? Like this is question 3. I guess maybe I put question 2 here. Is W2 given W1? It's very simple, right? Question 2 is very simple, but yes. Question 2 is that? Yes. Yes, that's right. Yeah, it's the same. Yeah, it doesn't matter the index actually. HW2 given W1 will be the same as HW2. Wait. It may or may not. Okay, that will be careful. Like HW2 given W1 will be equal to HW3 given W2. But okay, just looking at the model, I'm not 100% symmetric. Actually, maybe it is, maybe it's not. On top of my head, I'm not even sure. Oh, but yeah, you're right. Yeah, it should be because I have yeah, you're right. HW2 W1. Yeah. It should be like for Mookie's problem. Like it should be the same. Like think of that because yeah, you guys right. Because if you write it this way, this is stationary. Yeah, it should be the same. Yeah. Q2 and Q3 are not the same though. You need to be careful. That's why I asked you to solve Q3. No, actually think of that. That's the thing. Like today's weather, assume I'm in day 2 now, and I know yesterday's weather. Now I have a better prediction of today's weather, right? Now I don't know what's today's weather, or like okay, or I should say like, yeah, it's okay. But if there's someone from the future know what's the weather tomorrow, if I have both information on both sides, I should increase my chance of knowing what's the weather today, right? So actually, you should expect HW2 given W1, W3 should be smaller than HW2 given W1. See. Oh, how much break time? 7 minutes? Wait. For one thing, like no. 2 days. I guess that's the same question like how long mentioned earlier. You still have the 2 days weather will be depend on tomorrow. In all probabilistic model, there's no causation carve model into the model there. So like for modern like or like canonical like probabilistic model often used, you cannot more or less cannot represent the causation. So you cannot, yeah, basically future, yes.
Chang,
Yes.
I had a question.
Yes.
The question is that entropy of W2 given W1 is equals to entropy of W2 given W3. Does that still hold if W1 is rainy and W3 is sunny?
It yeah, it's not like, be careful like when we write the or like be careful like the definition is like that. Like let's say if I write HW2 given W1 like that, inherently like we are actually doing a weighted sum there. Like if you remember what we okay, we have more elaborate last time, but this is actually is same as I saying like what's HW2 given W1 is sunny, probability of sunny, or like probability W1 equal to sunny plus probability W1 equal to rainy HW2 given W1 equal to R. So so when you say given something like that, probably you mean this, right? Is that what you mean?
Yes.
Yeah, so it is not the same because like whenever we write like this, it's inherently already is an average. So it's like an average, on average, like knowing already W1, what will be the amount of information remaining in W2? And
Okay.
this is actually quite intuitive because you look at these two expressions. There's some chance that W1 will be equal to S, right? So if W1 equal to is sunny, then like the remaining information is this. And therefore, like the chance of to be sunny is this one. So I should be weighted by this one. And also by same token, it should add with this term also. So it's quite reasonable.
Got it.
So anyone managed to have the numerical solution also? Like maybe just for the first question 2 first, like anyone have a numerical number maybe? So maybe also, okay, like, so are you guys done with at least like the question 2? Like anyone have a numerical answer like for question 2, let's say, or maybe let me try to see if I really, it shouldn't be too hard, I hope. So anyway, I guess I can do it directly. So it's like, maybe as I just write like HW2 given W1 would be, oops, oh, okay, why it keeps sliding? So it's equal to probability of sunny, sum of probability of sunny, HW2 given W1 is sunny, right? Plus probability of rainy, HW2 given W1 equal to rainy, right? And then like when I'm sunny, then the probability is like I think the transition probability is 0.95, right? 0.95. By the way, this is like kind of shorthand notation. You also see the homework because the whenever we write this like hx or whatever, actually it only depends on the distribution, right? So therefore, it's equivalent to. It's understood that it's actually mean that hpx, right? The probability distribution of that x there, and if this is binary, then we can just even shorthand more, just say what's that called, like crossover probability, like p, let's say, right? Then it doesn't necessarily to be a crossover probability because it's symmetric, right? Entropy. So either p of 1 minus b doesn't matter. So anyway, like I should have something like that, right? And plus like PR is h. What's that? 0.8 or 0. Yeah, maybe I will put 0.2 here, right? So then this is like PS. Let me see, like what's H, let me try to, I think PS is like 0.8 over 0.85. If I remember, like something like that, right? PS is like 0.8 over 0.85 or 16 over 17, something like that. And PR,
16 over 17, yeah.
Yeah, and the other one is like 0.05 over 0.85. And let's see what's H95. Let's see. I better define the H function, it's easier. Let's see.
Professor, I have a question.
Yes.
So when you took H of W2 given W1 is equal to sunny, you only took H of 0.95. But then there was also a 0.05 chance of, for example, rainy given sunny.
Yes, this is just a notation things that people get convenient because that when we write H 0.95 here, it actually means something like H 0.95, 0.05, something like that.
Okay,
Yeah.
so we will take both for both.
Yeah, because it's understood, right? Yeah.
Oh, okay.
Yeah.
Okay.
It's just lazy notation everyone use. Yeah, so it's like you saw that like in the homework, the second problem, like I said, yeah.
Yeah. Okay, thank you.
Yeah. Let's see. Maybe I'm overkill at, but I'm just writing a function to compute the H function. Let's see. But it shouldn't take much time. P. So let's make sure I'm right. Let's see. I don't know. I got something like 0.28. I'm not sure any of you guys try to compute it as also. I want to get the numerical answer because I want to compare with this second question right here. So it's a 0.286. I hope I compute correctly for the 0.95, and 0.2 is maybe if you can help me to verify also. That one is 0.722. So what I get, oh, it's actually it's pretty big. Yeah, I don't feel comfortable with this number. Wait a sec. Oh, yeah, I made a mistake here. This is not 0.5. Yeah, 0.95, 0.05. 0.312. Do you guys get the same answer? So that's the question 2 here, like H2 given H1. And so let me read some of what you wrote first. The question like is H2 given W1 is H2 for yeah okay that we answered that. So for Joe, let's see question. Okay, that was it can be written in terms of mutual information. Okay, so yes, yeah, you can write this way, but I'm not sure like what's in your solution is going to help. Let's see, like you say yeah, the problem is like, okay, Wasim mentioned that like I can wait for question 3. I can I can write like HW2 given W1, W3 as HW2 given W1, let's see, minus I W2 W3 given W1, right? So something like that, right? So, oh, I think like you have a typo that like it should be given W1, yeah. So question 2, yes. Now this is not, know that like I don't have Markov chain here. So if I have Markov chain here, like if I have Markov chain W2, W1, W3, then it will be equal to 0. Then these two guys is the same. But actually we know that the Markov chain is different. It's like W1, W2, W3, right? So given W1, these two are not conditionally independent. So it already gives you hints that like this is actually smaller than this one here. Should be strictly smaller, but let us try to do a just numerically compute what is this. So I have like HW2. Let's just do this first principle thing. Like it's kind of easier. So this would be like HW2, W1, W3 minus HW1, W3, right? So then the first term here is like HW1, plus HW2 plus given W1 plus HW3 given W2, W1, but because I have Markov chain, the W1 can be dropped. So I have something like that. And the second one will be like minus HW1 minus HW3 given W1. So I have these two got canceled. The point is here, like, note that like these two are the same. Now, the point is like this is actually not the same as these guys here. If this is the same as these guys, then I will have this will be just equal to HW2 given W1. So I will get these two get cancel. Then I would just, yeah, I would just have like, just this guy would be just equal to the answer in question to just equal HW2 given W1. So what was this one, HW3 given W1? So HW3 given W1. So let's look at the, we need to figure out the probability here. So just do it from first principle. Like what's, let's see. I have like, let's see like what is PW3 given W1. Like just look at all these cases here. So PW3 given W1 is W3 W1 over W1, right? So this one is easy. I know what is that. Let's see. And PW3 W1 is like PW3 W2 W1 sum over W2. So because I don't know how I figure out like the relationship of like W3 W1 directly, right? So I just add this dummy variable W2 here. This is going to help me. But as long as I marginalize that out, then I will get back this PW3 W1. Right? So far so good, right? So now with this, I know how I'm going to do that, right? This one will be equal to W2, right? And I have PW1 multiplied by W2 given W1, right? And PW3 given W1, W2, yeah. So what it means is I'm going to have like this is equal to, yeah, equal to this guy here. Now I can plug this back to this guy here. Then I have PW3 given W1 is equal to this summation over W2. Note that I'm summing over only W2, right? W1 is actually constant. I can pull it out. So PW1 here. And then I have PW2 given W1 times PW3 given W2. And over PW1 here. So this got canceled. So I will have something like that. And I can, let's see, maybe I just keep this number here, but erase the rest. I'm not sure I have space for this. But let me write a table here, like what's W, let's say W1 is sunny, let's say, so what's the PW3 that is a sunny and rainy, and let's say PW1 is rainy, whereas PW3 is sunny and rainy. So let's see. This guy here, actually, this is I go for all this, but this is actually very intuitive. This is really given. Let me erase this now. Maybe it's not that useful. It's actually like given my today, like let's say the first day is sunny, right? So let's say day 1, day 2, day 3. So first day, given the first day is sunny, then it can either be sunny again like second day, but it can also go rainy in the second day. And then I will end up like maybe like sunny again, like maybe second day is sunny, but the third day is sunny, and then the third day is sunny, or like I may be have also another path is like I'm going to be rainy in the second day, and then it turn it back to sunny in the third day, right? And the probability for this path here is let's see, sunny to sunny, I think is 0.95, right? And sunny to sunny again 0.95 again. So this should be like 0.95 square, right? Plus sunny to rainy, that is 0.05. Yes, 0.05, and then rainy to sunny, then it's 0.8, right? I think so. So that is like 0.05 times 0.8, right? And I also like, if I end up with rainy, then what's the probability? End up with rainy will be like this pathway. Maybe I use a different color. So if I end up in rainy, then I can go this way. So then the probability will be like, first is also like sunny to sunny will be 0.95. Then sunny to rainy will be like 0.05, right? And then like this will be like sunny to rainy is 0.05. And then rainy to rainy is 0.2. So I guess one thing that you guys should verify is like, does this make sense? Like when I add this up, like does it add it to 1? So it's like the probability, given like the first day is sunny, the probability for the third day to be sunny and rainy, this probability should add up to 1, right? I think it's like quite easy to see that they add up to 1. Okay, kind of. So let me just compute the numbers also. Let's see what's the numbers there. This is a 0.5 square plus 0.05, 0.8. This is a this one is 0.9425, and the other one is probably hopefully 0.505 something. Otherwise, it's not correct. 0.05 2. Yeah, that's good. So the other one is a 0.0575, right? And then now for this one, okay, I can do the same manner. If my first day is rainy, then I have a chart will be different here. My first day is rainy. I start with rainy here. So then I can end it up to be sunny. I can get first next day, like second day is sunny, then I keep to be sunny, or like maybe the second day is actually rainy and then become sunny again. So then the probability for this one rainy to sunny is like, I think is a 0.8, right? And then like sunny to sunny is a 0.95, and rainy to rainy is 0.2, right? So rainy to sunny is 0. Wait, I think yeah, 0.8. Yeah, yes. Right. So therefore, the probability for this guy is like 0.8 times 0.95 plus 0.2 times 0.8, right? Now you can also like do another path, like to get rainy. The rainy will be like this way and this way, right? Then for rainy, it's like 0.8. Sunny to rainy is 0.2, and rainy to rainy is 0. Wait. Sunny to rainy is 0.05. Yeah, I need to be careful. Sunny to rainy is 0.05. Rainy to rainy is 0.2. Rainy to rainy is 0.2. So I have this other one is like 0.8 times 0.05 plus 0.2 times 0.2. Yeah. So then the probabilities are 0.8 times 0.95 plus 0.2 times 0.8. That give me this is 0.92. Hopefully the other one should be 0.08, 0.8 times 0.005 plus 0.2 times 0.2. Yeah, that's good. 0.08. Okay, now we can come back to compute this down now. So I can erase everything here. And so therefore, like HW3 given W1 should be equal to HW3 given W1 equal to S, right? And this plus, so this is probability of S and probability of R plus HW3 given W1 equal to R. So that will be equal to 0.8 over 0.85 times, this is a H 0.9425, right? Plus 0.05, 0.85 times H 0.92. So the value is, let me just quickly. Okay. This value is equal to 0.3224. Oops, I already erased this other one. The earlier one, this one is actually 0.312 or something like that. Yeah, so you see like this, okay, this is indeed is like bigger, right? So this is bigger. And so therefore like this is actually equal to, I have like two of this 0.3212. So it's like, this is 0.302, something like that. So you guys are fine with that? So you see, so therefore like that's actually a drop, like it's a slight drop. So it's not a lot, but it's a slight drop, right? So you knowing both like yesterday and tomorrow's weather will help me to know like what's going on like today's weather, even though I already know like what's going on yesterday. Yeah. And some of you, I guess in the discussion I mentioned like for HW1 given W2 or like HW2 given W3. So yeah, because it's symmetric, I guess all of you already figured that out. Like if I have W1 given W2, for this setup here will be the same because everything is stationary. This is just HW1 W2 minus HW2 here, and HW2 is just equal to HW1. So it's actually just equal to HW1. So it will be just equal to HW2 given W1 as well. So that's and any questions like if if not, let me get into the homework problem then. Let's see, homework problem. I guess homework one, I don't know.
So
like,
I have a question.
Yes, yes.
So Dr. Chang, yeah,
Yes.
I have a question. So in this transition probability, so maybe, so because I have the background in physics,
Yes.
and this one is, just reminds me that it is a two-state system, like a spin, electronic
Yes.
spin.
Yes.
So in that case, we use the density matrix.
Or density matrix, yeah.
Yeah, and then the entropy is usually can be calculated by just calculating the trace of this transition matrix, density matrix. So I think that would be much
in
easier to
physics,
calculate.
okay, of course, I know only a bit of physics, not a lot, but actually I did a master in physics, but I kind of totally forgot everything basically. But basically, like I think like typically they talk about configurations, right? So in your statistical dynamics, like you, I'm in the model typically the each of the configuration you have like same probability, or like it will be depends on the what's that called, like the energy-based distribution. I forgot what they both.
Yeah. So actually, so for example, this W1, 2, 3 can be represented by the two-column matrix, so like a vector. And then the transition matrix is just 2 by 2 matrix.
Yeah, you can do that. Yeah, you can.
Yeah. So once we construct the 2 by 2 matrix and then take the trace, that'll give us just the entropy. I think it's much pretty easy.
No, I'm not quite sure about that.
I mean, the log, log of the density matrix, trace of log of density matrix.
That you're talking about statistical mechanics, right? Or like
yeah, but it's still exactly the same as this, because each day, the weather of each day can be represented rainy or sunny. It's like a spin up or spin down, or 1, 0, 0, 1.
So I think like many times like you assume that like because I only remember the definition in entropy, like in physics, like the only one I never really, I forget everything about, but they will use like just simply the number of configuration, like the entropy as a number of configuration, take the log of that. So in the sense that it will be assuming the number of configuration is like they're all uniform, or like all the configurations are uniform there. So I'm not 100% like they have that assumption or not.
That is only when the system is in equilibrium, but it's not in equilibrium.
Yes.
So the entropy is exactly the same as this information entropy. So that is
okay. So let's see.
Yeah.
You are saying, okay, I have this you have this transition matrix, like some transition matrix. I can take the trace of that, or like I should take the log of that first.
Yes, first the log of the density matrix, which is 2 by 2 matrix, and then take the transition. I mean the trace.
Wait, but you have the density matrix.
So density matrix can be constructed by just product of 2 row. I if I write
really,
it down,
this is
much
almost
easier.
like 20 years
anyway,
ago. I forgot.
The density, probability can be, So probability is just can be represented by 1 times 2 matrix. So 1 by 2 matrix. I mean, 2 row, 1 column. Yeah. So each column matrix represent each vector. I mean, the probability W1, W2, W3. Then you can.
Yes. Then okay. Then you have the transition, right? So let's have the transition.
Anyway, so I think it's much easier to compute this entropy if we use the matrix.
I'm not 100% sure, like because I think I saw that when people like do quantum information theory, But in that case, that of course I also forget of everything there. So I vaguely remember like they have some yeah, I cannot give you a good answer now. Maybe we can discuss it with it can be interesting also. But I'm thinking at least in this problem, like you have this transition here, it's not really for this one, like it won't be a let's see, like you have this space, but like how do you translate, like you take a pair like each time? So you're saying like, because if I'm doing transition here, like if I appear, like also have like the, so what you're saying, like maybe I have W1, W2 here, so I do a transition, I get like this like W3, W4, something like that.
So actually, so there is W1, it's not W1, W2, but W1 itself is the column matrix. And then secondary.
Okay, yes, it has the
W2.
probability. Yeah, okay. It has the probability, basically write down the probability distribution here.
Right.
Yes.
So
That's the
Sunny
probability.
or,
That's a P
Sunny
here.
or Rainy.
That's the transition here.
Mm-hmm.
Maybe that example, like for example.
This made the that'll give us W2.
And this is like P. That's exactly like the steady state probability we talked about earlier, right? Is that like
right.
And
then we can calculate HW by just construct the density matrix, which is the product of this the two matrix.
Let's see if I just Google quickly if I can recall anything about my 20 years old. Yeah, but okay, yeah. Yeah, but I guess like the entropy is not the same. There, because like that's a classical entropy. It's like if you remember, there's some pure state and like mixed state, right? And this classic entropy there, like is probably is representing like things in the mixed state and not in the pure state. Yeah. Yeah, but my stat mech is really bad. I'm also like the
It's okay. It's okay. I just wanted to comment.
Yeah.
The mathematical similarity.
It's
from my background.
Of course that's the von Neumann entropy, right? That's exactly why von Neumann told Shannon like they should call it entropy, right? So I think you are saying that okay, I'm have the density matrix. Let's see. Oh, but it's actually the same. It's the same. Okay. Now it's exactly the same. But note that this is like in stat mech, right? Because in stat mech, the eigenvalues are actually the probability. Or yes. So therefore, like I think you are saying something like the trace of this wall, the density matrix of wall here, right? Is that what you're saying? Like the entropy is like that. Yeah.
Yes.
Yeah, but because you have the representation there, like in stat mech, is like you have the eigenvalues there is like actually the probabilities, right? So when you do the trace of this thing there, it's the same as the sum of the eigenvalues there. And the eigenvalues themselves are the probability. So we are doing the same thing, exactly the same thing. Yeah. So yeah, I think so. So okay. Anyway, there's a little bit digression. So any other questions?
I just wanted to know that what is written inside the brackets of H? Is it 0.9425?
This one 0.92, you say?
Inside the brackets of the expression for which you calculated the question 3 answer.
This wait.
What is inside the brackets of H?
Is that this one and this one? Is that the last line here?
Yes.
Yeah, 0.92 and like 0.9425.
Okay.
This is it's here. Yeah, so and this will end up like 0.002, as I said, like that. That's basically you get, yeah, you get a little bit gain, like knowing also the future if you want to predict the weather today. And let me go back to the homework problem. Like I need to find my question. I forgot like the question there. Oh yeah. Let me go through like that quickly. You can ask me any question though, like if you want to stop me anytime. So let me just plot like again like what we have, like the model is like something like that, like W2, W3, and we have the temperature here is kind of like we're observing like both of these is T0, T1, T2, T3, and so on. So the first question, like the A part is like asking what's the okay, let me finish that. I'm thinking like, honestly, it's actually a good time for me to talk about data processing inequality because we just showed this thing here. So, okay, I'm sorry, like, let me still like maybe before talking about the homework, like talk about this data processing inequality because we are already here in the sense you are seeing that from this question here, we have an interesting observation, right? So basically when we have a Markov chain here, I have a W1, W2, W3, and so on. So I have Markov chain like this. So let's say if I try to predict W4, my prediction of W4 given W3, as I said, like because of the Markov property, W4 given W3 will be just, or like W3 given W2 will be just the same as W4 given W3. Now, also like from what we compute earlier, we also see that like actually HW4 given W2, this value actually in general will be bigger than HW4 given W3. So you can quite easily understand that also. You can think of this as like when you have a Markov process, you keep on losing some kind of information. Now you're trying to predict this guy, like out of something like small distant past, like for example, you try to predict the weather now. If you use the data like 5 days ago to predict the weather today, it definitely is less accurate than like you're trying to predict the weather today using yesterday's data. So this is just precisely describing that. The uncertainty that you have knowing the information further like many days before will be like bigger than like more immediate past states information. So is that clear? So of course we're going to show that this is like in general called like data processing inequality. Typically it's given another form, like you will have like let's say X, Y, and Z. So as I mentioned, if I have this Markov chain here, so again, like this is called data processing inequality, I will have like, I just said like HZ given Y here will be less than HZ given X here, something like that. And typically it's written in another form, it's like the mutual information of like Z and Y will be bigger than the mutual information of Z and X. So it's like this is these two are essentially the same. Let's see, is that I can easily, yeah, because Z, wait, but Z depend on X. Yeah, Z depend on X, kind of like through this Markov chain, right? So like think of this tropical island model again, like many days ago, the weather still like kind of correlated to the weather today somehow with the model, but with the Markov chain, like hooking everything together, the weather closer to today, like less distant past, will have like more significant influence. So let's see how okay, this two is equivalent because I have essentially H Z given Y is equal to H Z, or like okay, or like maybe I write like this, like I C given Y, this guy here is equal to H Z minus H Z given Y, right? And this guy is equal to H Z minus H Z given X. So therefore, like you cancel these two terms here. So you see like these two actually equivalent, right? So if this guy is bigger than this guy, then minus this guy is bigger than this guy. Therefore, like this guy is bigger than this guy, right? So now let's show that like why we have this data processing inequality. So we have the data processing inequality. Just thinking like we have the conditional independence, right? So I have, let's see, I X Y, sorry, I X C given Y is equal to 0, right? So we have the conditional independence here. Now let's see if I add I X Y, let's see, what do I get? By train rule. So I guess I didn't show this kind of train rule, but you have I have train rule something like I X Y plus I wait, actually maybe I don't write it correctly, this one. I X Y plus I X Z given Y, that should give me I X Z and Y. Let's see, is that right? Is it I X? Yeah, I think so. So this you can just show that like with the definition itself, this is equal to H X Z minus H X Z given Y here. So therefore it's equal to H X plus H Z given X, right? Minus H X given Y minus H, yeah, minus is correct. Minus H Z given XY, right? So then I group this side here, I got like I X Y, and I group this side here, I got like I X Z given, wait, I X Y given Z, I guess. Yeah, I X Y given Z though. Let's see, did I make a mistake somewhere?
The first equation, should it be IXY given Z?
Oh, wait. I'm getting confused myself. So this one is like I z y given x. Yeah. Okay. Let's see. I see y given x. It's not exactly this form, but yeah, you can massage. Okay. Let's see. I see y given x. I x y. I see y given x. I x y. I see. So, 6 y I. Yeah, actually this y is I'm wrong here. Yeah, this is y. So this is y. I see y. So the lesson learned here is like if you are not sure, like just write it down. Like it's like 2 lines of cup equation, then you will figure out which way is the others. So yeah. So but I find that it's difficult to remember this kind of stuff. Maybe you guys are better, like have better memory, but I can only remember this like the because you can draw this Venn diagram to remember this, right? So this the mutual information like between like ixy is equal to hx minus hx given y. This kind of stuff I can remember. So but anyway, so this kind of chain rule, okay, I just show that like if you are not sure, like you can just write it out yourself. Like it's quite easy to figure that out. So but let's see, I have like yeah, so therefore like this is also like I have instead ix given y, right, I have I x z given y plus I. So this is like quite confusing to me. Like so now it's like I should convert C to x, like y to z, right? C to x, y to z, y to c. I see here, and x to y. Okay, that's good. So something like that. So this should add together should be equal to I. Yeah, I x y c. Yeah. Okay. Yes. Okay. I think I'm correct. So now then maybe what I want is that maybe I don't want to add this. Maybe I want to add something else. Is that I know this is equal to 0 here, just because of the Markov property, because of the Markov chain there. And so I will just add IYC here. So if I add IYC here, this together, I will get IX, Y, Z here. Now I can split it in another way. So I will split this again as IX, Z plus I, Y, Z given X, something like that. Now, because this is 0, so therefore it means like this guy is bigger than this guy here, right? So therefore I will get I, Y, Z is bigger than I, X, Z, or bigger than equal to, like in general. So this again, like the things I just show you guys is known as a data processing inequality. Again, like what you think of, like if like you continue to have this information flow, and you are trying to like predict the current variable given some previous like variables, then of course like given the variable closer to you will be like more useful. Like there will be more mutual information between the nearby variables from the variables like farther away, more distant paths. So okay, that is a little bit digression before we talk about homework, but I guess this is something I like to talk about anyway. I think it's this time to talk about that. So any question or so? Okay, let me. Oops, I have 20 minutes. I don't know, to less than 15 minutes to go through the homework now. So, but let's see. So let me go back to the homework again. So I guess most of you guys are okay with this like HT naught, right? You know this HT naught is just equal to HT1 is equal to HT2 and so on and so forth. But this one I have is equal to expected minus log PT, or just equal PT0. So the problem if you guys say you don't actually compute this PT0, but make sure you really actually compute the PT0 there. So you I find that like several of you like you ended up like compute minus log PT0 given W log is equal to Sunny, and then add that with like minus log PT0 given W log equal to Waney. So many of you compute something like that. And for those who got like the value is say 5 point something bits, like most likely that's what you computed. So just make sure like that you are not supposed to and a very reasonable check is like once you get this probability here, like PT here, this PT here should be a probability distribution of the temperature, right? So therefore, if you sum over the temperature, you should give you 1. So, and of course, like when I write this one, what I mean here is something like PT, maybe I just write PT is log PT minus sum over T here. So this temperature is like from, I forgot, like 20 something degrees to like 30 degrees, something like that. So, and maybe I just erase this bounds here. So sum over all this should be equal to 1 here. No. This should give you the entropy that's equal to the HT here. But if I just sum over this PT here, it should give me 1 here. Just if you make sure you get this, then you should be fine. But as I said, several of you like did something like sum over W here also. The problem if you sum over W here, the sum is like outside this. Know that like I have this sum should be inside here, right? Because like your PT is equal to PTW sum over W, right? So therefore, this thing here, this sum here should be inside this log here. So many of you like pull this log summation outside, and that's why you get the wrong answer. So is that clear?
I had a question.
Yes.
So in question number 1, HT naught,
yes.
we are basically asked to find the entropy for steady state temperatures, right? Temperature probability distribution, steady state.
Yes. So therefore, you need to figure out the PT first. Maybe. Yeah.
Okay, got it. Thank you.
Yes. I mean like PT0, like when you sum over all the temperature, it should be sum up to 1. So, okay, let me just maybe like, I'll share the screen instead, like maybe just, could be more helpful. Let me. So let's see, like what I mean is that if you remember, I have the temperature So let me just write like this. I have the temp. Let's say I have the temperature. Remember the range is here. The entire thing is range is 22 to 35 degrees here. So I just make a vector. Let's see. I call like the probability here. Probability of rainy is like that. Sunny vector, rainy vector. Oh, yeah, but you need, yes. Oh, okay, thank you. Yes, I have it here. So the rainy vector, let me just copy it. So I have it here. So the rainy vector is like that. So then I have my PR is something like that, right? So it's like from 22 degrees up to 35, 34 degrees, I think, right? This is all rainy probability for rainy. So and you want to check like they actually sum up to 1, like they suppose sum up to 1. This is like the condition that when you're rainy, right? And then like for sunny, I have like sunny, let's say, also have the same length, like from 22 to 34. And then like I will have my probability is like that. Then against my sunny will be like have weather like that, the distribution like this. And also like the sunny probability should add up to 1. So then PT now, what's PT? PT should be, remember, like I have probability like, I think I say 0.96 or something like that. It's like sunny, and then like with like 0.04 or something is rainy. Right, so my overall PT should be like that. I should shut down my Cantonese input. So, and you can verify that also a PT should add up to 1. So it's very close to 1. Now my entropy, therefore, like I think I have this function here. Just define that. Oh, did I? Yeah. Therefore, it will be like 3.27, something like that. So that's for the first question here. And then for the second question, like you asked to, let's see, what's the second question again? Second question is like TCO given WCO, that would be easy, right? Given WCO is like just more or less the same thing. Probability of TCO given WCO will be like given W will be something like HT. I just omit the index there, like because it's known as like for the same day, right? W is like sunny, right? Times probability of sunny plus HT given W is rainy times probability to be rainy, right? And then therefore, like this will be equal to simply H function. I already have this PS here. I got earlier times 0.85 plus H function 0.PR 0.05 0.85. Oops, what's the problem here? Wait a sec. Oh, okay. Yeah. I defined the. Let me change my function a little bit. How do I change that? Let's see. That's a little bit painful. How do I drop that? Like, do you guys know? Okay, I don't. My NumPy is not exactly so good. Let's see. If I want to remove P is equal to 0. Okay, something like that. Let's see. MP delete P and P where P equal to, hopefully this will work. Yeah, that works. So it's like 2. Okay, thank you. So yeah, that's a 0.97. That's like for the second question here. So for the third question, like we look at T1 given W0, right? So this one like we need to be very careful to deal with that. I think like many of you guys, I try to do something like HT1 W0, and I think some of you do something like that, sum over W1 HT1 given W1 W0, something like that. Some of you do something like that. But the problem is that when, or maybe you add a probability also like W1 here. But actually when you write this, like this is what you're computing here. It's not HT1 given W0, it's you're actually computing HT1 given W1 W0. And this is of course because of the Markov property, it's just HT1 given W1. And this will give you exactly the same solution as the previous question. So therefore, like for this guy here, like we probably, I don't know, like it looks like we may need to go back to the first principle, like trying to figure out, like, let's say what is HT1 given W0 given Rainey. So I may do something like that, like this one is equal to times P Rainey plus HT1 given W0 is equal to Sunny and P Sunny, right? Then we need to figure out each of this guy here. So for example, like this guy here is equal to, or like I should first consider the probability. Probability T1 given W0 is equal, or let me write this anyway. This will be equal to expectation minus log P T1 given W0 equal to wing anyway. So therefore, after all, I still supposed to compute this T1 W0 given CL. Yeah, this kind of stuff. So this, let's say I start with, okay, that Winnie, let's start with Winnie, it's okay. This will be like PT1, W1, given Sunny. So what I'm trying to do is like, I can consider this guy is that way, given W0 equal to Winnie, but then I sum over W1, right? Is that clear? So this will give me this, right? So, and of course, my W1 only have 2 states. It's kind of easy. I have like state equal to Sunny, right? And also have a state equal to Rainy, right? Now then I can expand like each of these guys here. So this one is equal to PT1, W1 equal to Sunny given W0 equal to Rainy is like PT1 Sunny given W0 equal to Rainy times PT1 given W1 is Sunny, right? And similarly, I have the same thing. PW1 equal to Rainy given W0 equal to Rainy. PT1 given W1 is Rainy. Now then we figure out these numbers here. Then let's see. I'm also like in a similar token, I can have like PT1 given W0 equal to Sunny is equal to PW1 is Sunny given W0 is Sunny and PT1 given W1 is Sunny as P W. Please don't bother with my uppercase and lowercase for the P here. So PW1 equal to rainy, W0 is sunny, PT1 given W1 is rainy. Yeah. So let's use what we have earlier. We have this PR, PS already. So let me compute maybe this one first, like, okay, this one will be a PT1 W1 sunny is like, I have this definition PS earlier, basically is that. Then P1 P0 is sunny, P1 is sunny, that probability is just equal to 0.95, right? 0.95. And then for this guy here, PT1 given P1 is rainy is just PR times sunny and then rainy, it will be like 0.05. Yeah. So let me just call this how do I call this? P maybe I just call it QS, like Q sunny, let's say anyway. So call this probability Q sunny. Now then therefore like the entropy for this part given sunny, this one is just equal to H function QS. Maybe I just call it HS, like whatever, like I call it HS here. Okay. Then I deal with this guy, let's say, is basically in the similar code token, I call it QR maybe, like PS times, that's basically, I have a probability transition like from rainy to sunny. That probability is like 0.08, right? And plus PR 0.2. Yeah. And then I have this, maybe I call it H rainy H function like QR. Right? Okay, I don't have any error here. That's good. Then the final final entropy will be just equal to this one. Right? This one is actually this guy here. Actually, I don't know why I introduced this HS and HR. It's totally not needed actually. And the probability to be rainy is like again like 0.05, 0.85 plus HS 0.85. Okay, that's what we get here. So therefore, like the conditional entropy is 3.258, something like that. So one thing like this also like show the data processing inequality, right? So when I try to predict something like farther away from the Markov chain, so I'm having like a larger the conditional the conditional entropy will be larger because like let me just share back like using my tab. So I have like less than 10 minutes, I guess, but so but do you guys have any question if like I just show? So because we actually have this Markov chain like W0, W1. Sometimes people put error in the Markov chain, but yeah, it's totally optional. T1, right? So therefore, I have like as we mentioned, the data processing inequality is like T1 given W1 will be like smaller than HT1 given W0. This in this like what we see there, right? So of course I have HT1 W1 here is just equal HT0 W0, right? And also like knowing something is always help, right? So therefore this guy here is always bigger than HT1, right? Oh, no, not always bigger, like always smaller than HT1, right? Because I know W0 is going to help, and this is equal to HT0. So therefore, like when you look at the questions here, you should, even your numerical answer may not be exactly correct, but one thing you should really check is like, you should know that like your solution in part A, like that comparing HT0 should be bigger than the solution in part C there, right? HT1 given W0, and should be bigger than the solution in part B, like HT0 given W0. Yeah, that's kind of expected, yeah. And I'm not going to repeat part D, like you know that it should be just equal to 0 because of the Markov chain. So now then, let me just really quickly finish talking about the question 2 and 3. I think we have enough time. That's good. So question 2 there, it's actually simpler than you expect. So basically the setup is something like that. I have x1 and x2, like it can be, for example, I can have x1 have some outcome A, B, C, and then x2 maybe have outcome D and E here, right? So I can X is like, you can think of this as like maybe 2 jar here. You have some, this is like some lottery ticket, have this name here inside this jar, you know. And sometimes I'm going to draw from this jar, and sometimes going to draw from this jar. And the names here does not overlap to overlap one another. So and I have some probability P drawing from this first jar, and then probability 1 minus P drawing from the second jar. And so therefore, like let's say, let me introduce a new variable. Let's say Z here. Z is basically the variable that like is equal to 1. Let's say if drawing from x1, and 0 if drawing from x0, x2. So then first of all, because this is no overlap, right? So if I look at hx here, I look at hx here, hx will be just equal to hx plus hz given x, right? So you all agree with that? Because if I saw the outcome here, if I saw that it's like, okay, I got a D here, I already know that, okay, it's like from jar 2, so therefore like Z is just equal to 0, right? So therefore like this is given X, this is just equal to 0, I can just add that. So this is like H Z X here, right? And then I can split it in another way, it's equal to H Z plus H X given Z, right? Now then like HZ is just like the probability of this guy, therefore it's just equal to HP, right? Or then maybe I can write P1 minus P anyway, right? And this is just equal to HP if we use this lazy shorthand notation. And this will be just equal to HX given Z equal to 1, P Z equal to 1 plus HX Z equal to 0, P Z equal to 0, right? So, and therefore like this will be just one of them is a P, this will be 1 minus P, right? And this will be just X given Z equal to 1, that would be just drawing from this guy would be just equal to X1, right? And Z equal to 0, that would be just drawing the second one would be just X2. So therefore like we have that, yeah. So any question? So I guess for the last one is actually, it's not difficult, but I just want to check if you understand the concept there. Basically, we have typical sequence. A sequence is typical if it's within this bound here, right? 2 minus n h x minus epsilon and 2 minus n h x plus epsilon, right? So if I have the sequence, I basically from the source that this discrete memory source have the probability drawing a con that is a hat, like probability of hat is equal to 0.7, I guess. And I say like I get a sequence that have like 70% of hat. So basically the sequence is like a 10,000 name sequence, right? And I have like 7,000 of them in a hat. And then I have like 3,000 of them a tail, right? Now the probability of this sequence, like I call this X forever, like probability of this sequence here is equal to 0.7, 70,000, right? 7,000, right? And 0.3, 3,000, right? And this will be equal to 2 to the log 2, okay? 2 to the log 2, this thing, right? So because this is log 2 and 2 to the power, so I just inverse function to one another. I can just write like this, right? 0.3, 3,000. And this will be like, because log product will be just equal to sum of log. So I have like log 2, 0.7, and log 2 power of that will pull it down with 7,000 here, and then plus 3,000 log 2, 0.3 here, and that's equal to 10,000. I put a minus sign here, minus 7,000 over 10,000 will be 0.7, right? 0.7 log 2.7 plus minus 0.3 log 2.3 here, right? Now this thing is precisely is equal to entropy, right? Is equal to hx, right? So therefore this is precisely equal to 2 to the minus n hx. Then of course, for no matter what kind of epsilon you pick, like that sequence will have the probability within this range here. So therefore will be typical. So I guess I'm pretty good with time. 1 minute late, I guess over 1 minute over time. So do you guys have any questions? Oh, okay. I didn't pay attention to chat. I'm not even sure if you guys have any. So, let me see. But I guess yeah, no one say anything, I guess. So yeah, I guess then maybe next time we'll talk about really talk about K divergence then. But I guess it's a good good session to review everything like up to now. Yeah, I'm thinking that maybe I'm not sure I will give him homework. Maybe I will give it later on. I don't know. Anyway, so I'll see you guys next week then. If you guys don't have any questions. Okay, bye-bye.
Thank you.
Thanks.